Thank you very much, Alberto. Thank you, Juan, for organizing this nice meeting. And right, indeed. So this is basically the first part of a two-part talk, in a certain sense, regarding this joint and ongoing work with Fedor Pakhomov from Ghent. And indeed, so the first part will be about the reverse mathematics of this principle of well quasi-order and better quasi-order theory, namely Nash-Williams theorem for sequences of finite range, for lack of better words. Okay, so the rough plan of the talk, this first talk, so to speak, is, well, first go through some basic of well quasi-orders and the reverse math in some sketches. And first of all, let's say, if you're completely new to the subject, why we should care at all about well quasi-orders, and then some fundamental results about them, namely Higman's lemma and, well, Nash-Williams results. Here I should do that, I should have needed another S because, well, there's plenty of things that Nash-Williams did to in this area. Then we present to the best of our knowledge, new just combinatorial proof of this result of Nash-Williams, the one in the title. While carrying out this proof, we will see that there is essentially all of the proof goes through in ATR0 except for one bit. We will identify that bit and then spend the rest of the talk essentially carrying out that proof in the appropriate system, in the system as we want, which is ATR0, and I will say why we want that. Okay, so first of all, the definition. So, just to make sure that everyone is on the same page, you need to fix notation if nothing else. A quasi-order, henceforth just QO, is just, well, exactly what you expect. So it's a pair of a set and a relation, binary relation on that set, such that this relation is reflexive and transitive. So basically, don't require anti-symmetry, which is where the quasi, the Q comes from. But for the rest, just think of them as orders. And I say that a quasi-order is a well quasi-order if, well, intuitively, if it has no infinite anti-chains and no infinite descending sequences. Or, well, another way of thinking about it that we will sort of need is the following. So, however you take a sequence of points inside of Q, inside of Q, then you will find I less than J, such that in a certain sense their order is copied inside of Q. So I is strictly less than J, and f of I is, well, less or equal than f of J, which can also more snappily be said by saying that no Q sequence, or no sequence taking values in Q, is bad. Okay, actually there will be several other definitions of well quasi-order, well, not just in reverse mathematics, in mathematics period. But yeah, they are essentially all equivalent in ESI0, and, well, in this audience, I'm certainly not the one more indicated to speak about this particular subject. But yeah, so as I was saying, essentially the base theory for the rest of the talk is ATR0. So we are, let's say, we don't really care what definition we use for, but yes, I would like you to have in mind these two. Okay, so why do we care about well quasi-order? So long story short, they crop up everywhere. So if you don't believe me, that there's a paper by Kruskal in '72, basically called well quasi-orders, a frequently discovered concept. If you're from Ghent, another way of noticing it is to have any conversation of meaningful length with Andreas Weiermann, who will convince you that the well quasi-orders indeed are ubiquitous in mathematics. It depends. So there are various definitions. So I'm not entirely sure whether there's any definition that requires ESI0 in order to be proven equivalent, but there are several possibilities. I think some of them are equivalent over B sigma 2, some of them require something between CAC and ADS. Sorry? Right, for instance. Yeah. Or Ramsey theorem, for instance. Or W, So ESI0 is just an upper bound. I mean, it's one of, let's say, the smallest of the big fives that I'm sure will suffice to make everything collapse. This is why I chose it. This thing? Nash-Williams, sure. Yeah. Yeah, but here we're talking of something else. We're talking of definition of well quasi-order. I thought that was your question. Sorry. Yes. Okay, yeah, I said that I will justify later why ATR0, and yes, I mean, part of the reason is just we already know that ATR0 is implied. So not just ACA0, but ATR not. Sorry, okay, yeah. I thought you, okay. Okay, well, an example of where we could have seen well quasi-orders crop up let's see, during your talk, for instance, and maybe there's more about it during Andrea's talk, is considering a following, let's say, more trivial version of Goodstein process. So let's say, in general, sometimes you notice that well-quasi orders are very good when you want to, by and large, prove the termination of a process. So if we consider this Goodstein process, so you take a number n, you write it in base b, and let's say your step is just substitute the base b with base b plus 1. You don't touch exponent, you don't touch the coefficients, and then you subtract 1. Well, how do you show that this thing terminates? How do you show that this process eventually reaches 0? For instance, you could simply show that this guy here, so the sequences over n of finite length ordered with this ad hoc order, which you wouldn't really need, but surely does the job, is a well-quasi order. So in this case, what order does the job? For instance, you say that a string is less than another string if, well, either one is positive, strictly shorter than the other, or the length is the same, and all the components are not larger. All the components are below, right? And then you see that basically, okay, instead of writing n like this, you could see it as, if you allow also 0 digits to crop up, you basically see every number as a string of length em plus 1. And what you do in this process is basically, well, in the steps where you remove 1, you're happy, and then you surely, it's not that you go down according to this order, but you surely never go up, or there's some carry to take care of, but still. So the point is that this process never brings you, never makes you go up. So why would you need this guy to be a well-quasi order in order to show that that this terminates? Well, because if the process did not terminate, what you would have described would have been one of those bad sequences that I was telling to you about. And this is exactly what we cannot have in this order. So, of course, there's plenty of different ways in which you could show that this process terminates, but this is one. So we just reduced this termination process to show that something is a well-quasi order. But there are more meaningful examples coming from mathematics. I guess the first one that comes to mind is the famous graph minor theorem that says essentially that undirected graphs ordered by this minor relation is well-quasi order. Now I will assume that people know what a well-quasi order is, what the minor relation is, and what are the consequences. Why do people outside of logic care about this? Well, for instance, another characterization of well-quasi order that I said nothing about is that basically downward closed sets are finitely described. I guess, so if you have a well-quasi order, something like this, and you have a set which is downward closed set, which is downward closed according to your order, then in order to describe it, you just need finitely many elements, and this set will be basically everything which is not above these elements. So in particular, so it means that in a certain sense, Wagner's theorem, so the characterization of the planar graphs as the graphs not embedding, let's say, not having K33 and K5 as minor, is nothing special. Every set of graphs which is downward closed with respect to the minor relation will have this characterization. So you know what finitely many elements you need in order to describe it, but you know that you will be able to describe it with finitely many forbidden elements, essentially. So in general, this may not much to convince you, but the general idea, at least for me, so, let's say in well-quasi-order theory, one of the driving ideas is that you want to show that quasi-order actually are well-quasi-orders. And one natural question to ask is, well, so if I start with a well-quasi-order, what sort of operations D allows me to define something else, but still preserve well-quasi-orderness? Okay, for instance, in this case, we start with, you can see this thing as saying basically what? We start with n, just the natural numbers. You know that thing is a well-quasi-order because it is a well-order. And you define something larger. If you had a result, a general result that tells you that the operation you applied just gives you a well-quasi-order because it is a general theorem, then this thing is proved automatically. And in a certain sense, this is what the next slide is about. So one of these principles is Higman's lemma. And for this, I will need another bit of notation. Okay, so just given a quasi-order and two sequences U from alpha and beta are ordinals, and U and V are just Q sequences. We see that U embeds into V if there's it's just what you expect. Okay, so if there's a strictly increasing sequence from the domain of the first one to the domain of the second one, that tells me how to compare the element in a certain sense. So I mean, so again, an example is probably better to explain this sort of thing. So suppose that the first ordinal is 3, the second ordinal is 5, and okay, so I write this to say that U is the function mapping 0 to 3, 1 to 5, 2 to 2, and V same thing, but well, this thing. Then we have that U embeds into V via, well, I can choose the map in at least 2 ways, right? So I can say that the first component, so 0 is mapped to the first component, so basically we are comparing 3 with 3. Then the second component, the second component is compared with the third component. So 5 I compare it with 7, and 2 I can compare it with either 3 or 4. So either the third component or the fourth component. So if instead we chose another football formation, that we would lose a comparison here. And basically Higman's lemma tells you what you expect, so to speak. So if you take a well quasi-order, as long as you consider sequences of finite length, you still end up with a well quasi-order if you use this sort of comparison. Okay, and in particular, I should say, okay, you shouldn't go back, but I could have used this order here, and this would still do the job. So Higman's lemma does prove that this would same process terminates. Unless I said something false. Which example? This one? F equals 1 to 3, I mean that f of 0 is equal to 1, f of 1 is equal to 2, and f of 2 is equal to 3 or 4. So now if you look at v of, v of 2, v of 2 is equal to 7, and indeed you have the comparison. Everyone starts with 0. Yeah. Oh, yeah. I didn't say it, but yes. I'm assuming 0. Okay. Okay. Well, then there's an obvious question. I mean, why stop at omega? There's plenty of beautiful ordinals larger than that, but things fail immediately. So, and this is in a certain sense the problem with well quasi-order theory. So, well quasi-orders are extremely nice objects, but they don't enjoy the strong closure properties you would like them to have. Okay. So, it was an example by Arado in 54 already. Who found a well quasi-order Q such that if you go immediately beyond omega, so if you take any sequence of length omega, that thing is already not a well quasi-order. And then it's where Nash-Williams came in. So, okay, I'm calling this Nash-Williams theorem prime. You will see why. You're allowed to forget about this anyway. So that show that, okay, so these things, so the result that we want, so this basically, the set of sequences of arbitrary length is a well quasi-order if and only if Q enjoys some better closure properties, namely it's a better quasi-order. I mean, we will see a more technical definition later on, but let's say, if you just want to have an immediate picture, so this is why you want better quasi-order in your life, so to speak. And this could also be used as a definition. Yeah, this is a characterization. It doesn't really tell you how to work with them, but this is why we like them. But he also proved, well, he proved it before, that some form of, let's say, without introducing better quasi-orders at all, some form of Higman's lemma still survives, which we will call Nash-Williams theorem with the F for finite range, namely that if you, let's say, allow the range to vary, if you allow the domain to vary arbitrarily, but you restrict the range to be finite, then you still move, let's say, with this operation, you still move well quasi-orders into well quasi-orders. And this is what we want, let's say, and we want to study the reverse math of this today. Okay. The implication of right to left is the one, yes. I wouldn't say so. Well, that it implies ATR0. Okay, so yeah, how easy it is.
Not in a finite. Why is ATR not?
No, well,
More analysis.
so that better quasi-order, that Q better quasi-order implies, so it basically follows from what we say today, that you can prove it in ATR0, this thing. So this,
the implication implies.
if the implication,
Which theorem you're looking at?
and WT prime, I assume you're asking for about this. So the implication from better quasi-order to this thing. I'm not sure of the reversal, let's put it this way. So from going from better quasi-order to say that this thing is a well quasi-order goes through in ATR0. It should also be true that it implies ATR0, but it should. But yeah, everything implying this essentially should imply ATR0. Yeah, okay.
Well, except it must
Yeah. Everything else should follow. Yeah. No, you're right. Yeah. Even if you, yeah, okay. Yeah, right. Being well quasi-order implies ATR0. Yeah, it's true. Right. Well. Yeah. That's your result essentially, because it should follow that you can, that you have comparability of well orders essentially. No, it's true. Yeah. So you should have said that yes. It is the implication is equivalent to ATR0. And actually, I have it on the next slide. They definitely should. It should. No, for the other one, I'm not sure. So that it goes.
From Nash-Williams.
Right, and this is why I'm putting this prime here. So the theorem is more, yeah. Which
So
is
in that case, left to right is.
in that case, yeah, which is why I'm stopping here. So if you just have well quasi-order, I'm less sure.
You also showed this. You also showed
this thing,
this.
yeah.
Earlier when you transform.
Right, so here with the attribution, I'm a bit confused because there's some of these is also attributed to either Pouzet or Julien. But yeah, I mean, someone of those three also did.
Pouzet, actually.
Maybe Pouzet, but yeah. Okay, so indeed, this is what I should have said immediately. Essentially, so that if you look at the reverse math of these results, well, there's basically Higman's lemma, which is, so to speak, an exception. So this is equivalent to ACA0. Here also the attribution, I'm not entirely sure to whom it should be given. So here I'm referring to the paper by Schutte and Simpson, but Simpson I'm not sure. Then over RCA0, either of Nash-Williams theorem or the finite version of it. Okay, yeah. So the reason why I was using prime before is this. So what Alberto was saying. So what was proved, let's say, what we consider to be Nash-Williams theorem is the statement with well quasi-order instead of better quasi-order. So any of these things, but also the weakening that we had before, implies ATR0. So Shor proved it. Well, it turns out that it was, he proved it over RCA0 plus a sigma 2, and the assumption of a sigma 2 was removed by Anton Freund and Davide Manca more recently. And then Alberto showed that in pi1 comprehension, you have, pi1 comprehension is enough to imply, to prove Nash-Williams theorems. And this result was in a certain sense later improved by Tausner, who used in a certain sense an ad hoc system. So it is a weaker system, but as he himself says, the proof is essentially the same. And I care about the proof being essentially the same because, well, in a certain sense, these proofs highlight why it is difficult to deal with well quasi-orders and better quasi-orders in reverse math. So the classical proof that something is a better quasi-order especially rely on results, relies on some forms of the minimal Bedder lemma, which is probably hard. And they tend to be very strong. As, let's say, in a certain sense, a feature of, well, this talk and of the project in general is to, so to speak, substitute the use of minimality arguments with proof of well quasi-orderness of, well, instead of Q, of structures related to Q. And I will be more precise what I mean about this later on. Okay. today. Okay, so I should say something about the meta theory. So I will not stress too much about where we are proving things in, but let's say I guess it's better for everyone if you think of the base theory to be ATR0 set. Why I care about sets will be clear in roughly 5 slides time. But yeah, anyway, some variation of ATR0 does the job. This is what we claim. Okay, so what are these better quasi-orders? Well, the main idea is to mimic the definition of well quasi-orders, but what we forbid, instead of being sequences, instead of being bad sequences, is something else much more complicated. Okay, so amongst the various things I should be grateful to Alberto for is that he already introduced fronts. And I assume that everyone is now familiar with that concept, right? So, I mean, a snappy way of defining them would be to say that a front, for me, is a subset of, okay, so you pick an infinite subset of the natural numbers, of omega, and then you consider a minimal closed covering of it. And this is basically your front with the usual box topology. In more practical terms, I would be just repeating what Alberto says. So a front F is a subset of x to the less than omega, such that what? Basically, yes, I mean, its base is formed by infinitely many elements. So these, yes, the union of F of all the elements you take is X, the infinite set you started with. Then you want F to be an anti-chain with respect to the relations of being an initial segment of, and again, so here we are mixing the perspective in which we see strings as sets and strings as strings. And then we also want that for however I pick an infinite subset of X, I can find a finite initial segment of it inside of my front. Examples, I'm just repeating, the standard examples are, well, if you take singletons, you're happy. If you take sets of cardinality n, so I mean subset of the natural numbers of cardinality n, you're also happy. Schreier's barrier, I don't want to define it, but well, if you consider that is also a front, and it will be even more, but we don't care. Okay. So the annoying thing about, well, see, yeah, there's several annoying things about fronts, but well, if you want to copy, to mimic what we were doing with well quasi-orders, see, so the nice thing about omega is that it comes naturally embedded with an order. We don't have any order on fronts, basically. So the idea is that fronts will be our new omega. So how do we order elements there? We don't really order them. So we just put a binary relation in it, which will not be transitive in general. So we say that sigma and tau belonging to a front. We say that sigma is a predecessor of tau. When, basically, so if I can find an infinite extension of sigma, let's call it y, such that if I remove that initial segment, so if I remove the first element of this y, tau will be the initial segment of this set here that is in F. So for instance, if our front was pairs, we would have what, that 2, 3 is in a triangle relation with 3, 5. But it is not in a triangle relation with 2, 4, for instance. I mean, I'm not particularly aware of any intuitive way of presenting this sort of relation, but it turns out that this is what you need for. Okay, and finally we say, like, what is the analog of bed sequence? It's bed array. So we say that a function g from a front into Q is a bed array if, well, if two things being in this relation implies them, let's say, yeah, implies them not being in the Q relation. Hmm? Does it follow from the, yeah, but so here I'm giving a new definition. It's a separate definition. So I'm saying, so here is basically a snappy way of describing it. Here I'm starting afresh. You say, okay, I could define fronts as, like this. So you pick your infinite set, you pick F subset of x to the less than omega. What do we require of F? Well, we require that the...
that condition that you just pointed to,
yes?
isn't that implied by...
So being an anti-chain and that there is an F with... well, it's true. Okay, yeah. So I could do without it. Yeah, okay. Yeah. So, sorry. Okay. Discovering condition, yes. No, yeah, true. Okay. Excellent point. Thanks. Okay, and then the, let's say, analog of Ramsey theorem for better quasi-order is Kloppen-Ramsey theorem, which tells you that for every front F and coloring of F into colors, there is an H so that if you restrict F to H, this restriction is monochromatic. Now, what do I mean by a restriction of F to H? I mean, so for me, F of H are all the sigmas in F that also happen to be subset of H. Just an infinite subset of omega. So I guess, I mean, maybe I could have made everything clearer just by saying that the base of a front is always omega, but then you cannot really phrase this thing properly.
I was just wondering.
Right. Natural numbers, yeah. Exactly. There's no relation with fronts and the relation is just given by arrays. Yes. As long as it is infinite. Yeah. Okay, so an easy consequence of this thing is, for instance, that, well, then finite orders are better quasi-order. Just if you look at this definition, there's, let's say, no immediate reason why any poset of cardinality 4 should be a better quasi-order. But let's say if you apply this thing 3 times, then you see that indeed you can show that from any array G into anything with just finitely many elements, well, anything with 4 elements, let's say, then you can restrict it to be constant, and then you're happy. Okay. There are several things that I should be saying, but I'm not. Let's say this is a complicated theory that surely shouldn't fit in one slide. But well, this is the time I have.
Say that
Yes. Okay. Next, so we are approaching this, what I claim to be the new proof of Nash-Williams theorem for sequences of finite range. So we are interested in a particular kind of sequences, namely the indecomposable ones. So I'm saying that a sequence is indecomposable if it embeds in all of its states. I mean, you can write it this way, so it doesn't matter where I start considering the sequence, I will always be able to embed it into what's left. So in particular, I mean, so here I phrase it in general, but this will not work for any alpha, right? You need at the very least that alpha is in the composable ordinal itself. And it is a theorem by Julien and Pouzet, probably just Julien and Pouzet proved the other direction, but this paper are all in French, I'm not entirely sure where the attribution should go. And also I wasn't able to really find the original paper by Julien. But well, so it is a theorem that if Q is a better quasi-order, then every Q sequence is a concatenation of finitely many decomposable ones, which in a certain sense tells you what we care about these guys here. So these are the building blocks for all the other sequences. So as long as we consider indecomposable sequences, we are essentially considering all the other sequences as well, except for the fact that we might have to stick them together finitely many times. And this allows us to prove the following technical result, which basically tells that so if I have 2 sequences, what order are they? So if I have U and V, and I know that V does not embed, that U does not embed into V, well, this is basically just saying that then I can find just one segment inside of U, which is properly shorter than what we started with, and basically it's his fault if you cannot embed U into, well, any initial segment of V. So this guy will not be embeddable into any initial segment of V. And why is this the case? Well, the proof is a one-liner really. So if U does not embed into V, and then it's basically some delta's fault, so to speak, some delta plus 1's fault that you can't embed into V. You just have to, try it and you see it works. So the problem with doing things this way is that there's no guarantee that this guy is indecomposable, and we want to remain within indecomposable sequences. Yeah, but then you can use the theorem by Julien to say, okay, decompose this guy, and it will be, so decompose this guy, there will be finitely many pieces of these, and and one of these guys will not be able to be, I mean, you won't be able to, there's one particular element of this decomposition that won't be embeddable in any of the initial segments of V. I don't know if it makes any sense. It's just a matter of, it's trivial combinatorics to a large extent, but this is how we use this result here. Now, and this is in a certain sense the engine that makes the proof work. Okay.
I have a question.
Mm-hmm.
Do you know if
Yes.
do you know if it's all
The sequences are embedded.
you have a scattered
Mm-hmm.
and you
It could be true, but yeah, it should. It's not the final result, it should be one of the intermediate results, but yes. Again, I would like to check. Yes. Form a better quasi order. Okay, so just to remind you, this is what we want to prove. And well, so first of all, notice that if I sequence U as finite range, well, then the range is finite, and by what I said before, then it's a better quasi order. So in particular, we can apply the result from before. So every sequence of finite range can be decomposed into indecomposable, into finite remaining decomposables. Okay, so by Higman's lemma, or let's say, because it's obvious, we just have to show that, okay, so here I didn't say, but by this tilde I mean that we just restrict to indecomposable. So this is what I just said. So it is enough to show that this thing here is a, yeah, that this thing here is a well quasi order. And the proof then goes by contradiction. So suppose that we have, okay, this is a, we'll have to say something about it, okay. So suppose that we have a bad sequence in W, so I have a bad sequence of indecomposables, and we want to expand it to a function now. Okay, so here I should have removed the empty set technically. Okay, curse. I want to expand it to a function defined on all finite subsets of omega into this seemingly very complicated range. So I want to consider all the indecomposable functions with finite range, but I want to remove sort of the degenerate ones, so to speak. I want to remove the ones that only have length 1, which still count, and instead of them, I use Q multiplied with omega. And I mean, you're perfectly right if you're enraged by how complicated this thing looks, but I mean, this cannot be really done without for a simple reason that I will tell you in a moment. And the idea is that we define this function h by recursion, preserving badness, by which I mean, so we start basically, so we already have this h defined on, let's say, level 1. So on this sequence could equally be seen as a function h defined on omega to the less than 2. Okay, so you stay at level 2. And at every step of the recursion, we define it on longer strings. And well, so this is what I just said. So at the first step is basically, in a certain sense, just rewriting what needs to be rewritten, in the sense, so if we have a sequence of length 1, we don't really want to use the sequence of length 1, we want to use basically the point that the sequence is describing, and then 0, because remember, I'm not allowed to use anything of length 1, I have to find something that lives in there. But if I'm not in this case, then I'm perfectly happy to keep whatever I had before. And this is the next step. So in a certain sense, like, as I was saying, this is the engine that makes the proof work. So at every step, you're basically comparing two sequences. So the idea is that you want to define h of n0 and k, knowing basically h of n0 and k minus 1, and h of n1 and k. So basically, whenever you want to define it on whenever you want to define h on something, of this form, you care about well, basically this removing the first element and this removing the last element. This is essentially what I want to say. Now, by this preservation of badness that I was very vague about, we know that for this sigma and tau, let's say, so h of these things will be v and u, of which we know that they're incomparable. Ideally, we want to go, let's say, one step lower. So we want to find shorter sequences that still preserve the properties of being indecomposable, but also being incomparable. How do we do this? Well, exactly with the theorem that we said before. So of V, I'm knowing that at the next step, I will just consider, well, a segment of it, in particular something shorter than an initial segment, and this is what we care about. So I want to find something within U that ensures me, that ensures that I will not ruin this incomparability relation. And this is exactly what we care about. So we have alpha and beta that will give me a shorter sequence, still indecomposable, with the property that I want. Now, why do I want this, why do we need to bother with this omega? Basically, it's because of the length. So suppose, for instance, that the first sequence, so U of 0, yeah, thank you, David. U of beer. So suppose that U of 0 is a sequence, let's say, that takes value 0 constantly. Okay, so yeah. U of 0 is just some Q repeated omega many times, and U1 is just Q. So this is a sequence of length omega taking just one value. This is a sequence of length 1 taking just one value. Now, okay, so this thing does not embed into this thing, but the reason why you cannot embed it is not because of the values themselves, it's just because of the length. So the reason why we really need to carry this omega here is because, well, incomparability is not just about the poset, it's also about the length. And this is the price you have to pay. So yeah, sorry, but blame math for it. Okay. So this is how we use the technical lemma. Okay. And finally, we consider F given by basically the points where you hit Q times omega. I don't want to prove it, but well, it's a routine proof that, well, F is a front, and thanks to this preservation of badness that we bother with so mightily, we also know that if we restrict H to this front, we get a bad array. Now, if Q was a better quasi-order, we would already be done. Because we know that if Q is a better, well, okay, so I know, let's say several people in this room know that if you start with a better quasi-order, if you start with two better quasi-orders and you take the product, that thing is still a better quasi-order. So if Q was a better quasi-order, we would also know that this is a better quasi-order, and we would have a contradiction because we would have a bad array into Q times omega. But this is not the case. Our assumption was simply that Q is well quasi-order, so there is some more work to be done. I mean, but there's a reason why this will come. I mean, yes, we have to say something about it later, hopefully. Okay, maybe not. Okay, now let's just forget about the second component. So we don't need omega for now. Let's just consider the values in Q that are taken. What we want to do next is essentially restricting the front such that if we look at this Q component, this thing actually do form a better quasi-order, and indeed it will be a well order for us. Okay. So we define this, other typo that I will not change now. So we consider this thing here. So, okay, I will not describe it, but so this is just a front. So I'm taking the first component, and then the thing that I put afterwards are just a thing that can conceivably extend this n inside of our f that was defined here. Okay, and then we define this coloring here. So we say that this guy is color 0. If G thinks that these two guys take the same value, otherwise we color it 1. Okay. Independent, yes. No, sorry, sorry. Yeah, I should have, so sigma 0, so the max of sigma 0 is less than the mean of sigma 1. Oh. Sorry. Yeah.
So then you can
yes, so there's one more typo. Yes, sorry, there's one more typo here. Yeah, otherwise it doesn't work. No, indeed. It wouldn't make sense. Yeah. Okay, so here's just the definition that I gave, and well, now by Kropp and Ramsey, we can find an homogeneous set H prime, and well, it cannot be homogeneous for color 1, right? Because all of these values, so by the way we set up the procedure, all of these values, so whatever value G takes, it will belong to the range of UN, of the corresponding UN. So the first component tells you basically where you're picking values, but there's finitely many of these values. So you're homogeneous for color 0. Okay, now we can define this H, this is H prime, this is almost what we want, and the point of this front is basically that now you're coloring, so if you restrict to it, you're coloring in a certain sense, so when it comes to the Q component, only depends on the first component, and now we're happy, because basically instead of having a bad array, we just have a bad sequence, and now we can use the assumption that Q is a well quasi-order. So now we can refine H prime to H, in such a way that R of H is a well order. And now we're done. Now we have a contradiction because, well, because we have restricted ourselves indeed to the product of better quasi-order, and we should have a better array into a product of better quasi-order, we surely cannot happen. Okay, now all the proof above can be carried out in ATR0, except for the bit we did not prove. So the Julien-Pouset theorem. Now I should also say, Alberto already proved this result, but in Python 1 comprehension. This was one of the various results that went through in Python 1 comprehension. So in a certain sense, the rest of the talk is dedicated to show that ATR0 is enough to prove this. So that if Q is better quasi-order, then every Q sequence can be decomposed into finite remaining indecomposable. And in order to do this, we introduce a fundamental ingredient, which is essentially the reason why I'd like you to think of the base theory as to be ATR0 set, namely iterated downward closed sets. So the main idea being that, so if you just look at all the sequences, this is a huge set which is very messy, and we want to look at something which is much tamer. Okay, and this will be given, yes, by iterated downward closed sets, which is basically, and you should think of them as follows. So your original quasi-order Q, you can think of them as your elements, and in a certain sense, you built the cumulative hierarchy on this Q. The reason why you put a dot is because we never allow the empty set to creep in, essentially. So we don't want the transitive closure of any of these elements to contain the empty set. That's a technical, I don't think we will actually see why this is needed, but trust me, it's needed, okay. Okay, so in a set, so we could define it as usual, like this way. So the 0th level of this hierarchy is just your elements, and whenever you go up, you take the power set, removing the empty set, and then you add back whatever you lost, and the limit stage is you take unions. Now, how do we compare these elements? So what we want to do is to put an order on this thing, and the way we compare sets in this hierarchy is the following. So there are some easy cases, well, there's one easy case in particular. So if X and Y already are your elements, you surely want the comparison to be maintained. Then if X is your element and Y is not your element, well, I'm saying, okay, so just consider the set containing X and compare it with Y. So you will have this comparison if this holds. And then, well, if you are comparing sets, then you ask that for every element of X, so you say that X is less than Y, if for every element of X, you can find something inside of Y, such that this X prime is below the new element that you found. Well, I mean, signitos below any other set that contains them. The third clause. No, so I'm just saying, so basically, so if X is your element and Y is not, then I'm saying, well, just compare them as sets. So instead of considering X, consider the set containing X. Yeah, and then you go back to case 2, which is why I put things in this order, but then I explain them in the other order. Because I forgot why I put them in this order. Yeah, okay. Okay, so let's just draw an example. I mean, someone here was saying that a picture is worth 1,000 words. So, and just consider this was it here, so by which I mean that 0 is incomparable with 1 and 2, and 1 is below 2. Now, V1 will look something like this. So I have my original sets, which indeed will be, so I have my original elements, which indeed will be very low in this set. Yes, and then I compare sets according to the relation that I'm given. So here you should see why I'm calling them iterated downward closed sets. So, for instance, 2 is equivalent to 2, 1. So I don't care about taking downward closures here. So if I take any representative, let's say, if I take any set and then I consider anything which is below that set, this doesn't change the order here. So if you remember, the order was something like this, well, 0, 1, 2. So I'm saying that the set containing 2 is the same thing as the set containing 2 and anything below 2. And the same thing here. So the set containing everything is the same as the set containing basically just maximum elements. This is where the terminology comes from. And then you just have to iterate this. Okay. And the idea is now, well, as promised, that I want to move from sets to sequences. I mean, the claim is that sets are better than sequences, that, well, I have to move one way, I mean, from one to the other. And okay, so here I'll probably be very fast about it. So there's a relatively easy way of moving from sets to sequences, which basically, I mean, you just have to take care of the length in a certain sense, which is basically just saying that you unravel sets. So well, this is the definition of the map iota doing this. So if you have a sequence of length 1, sorry, if you have a set which is just a your element, you associate with the sequence of length 1 mapping 0 to that element. If you have anything which is larger, well, I guess it's better to give an example. So you keep you know by induction that you have already defined iota on every element of your set, and you keep stacking those maps together, essentially. So let's see an example here with the same order as before. So this is 0, this is 1, this is 2. So for instance, iota of 0 is just 0. Okay, so here there's a bit of a clash. There's a lot of clash. Doesn't matter. So what is iota of the set containing 0? Now, judging by this definition, so we already defined iota on your element 0. What we do here is we concatenate this map omega many times. So what we get is the sequence of length omega taking value 0 constantly. Okay, so what happens if we do something allegedly non-trivial? So here there should be some dependency on basically how I choose to repeat elements, right? But so the point is that to modulo the right comparison, we don't really care. So here I'm just alternating between, let's see, choosing this one and choosing the other guy. And again, so by the previous step, we have defined the iota on this element here. We have defined iota on your element 1. So what we do is that we keep stacking it together. So here we start with a set, let's say, of rank 2, and we end up with a sequence of length omega to the, well, omega squared, essentially alternating, which keeps doing this. So it gives you 1, 0, 0, 0, 1, 0, 0, 0, and so on and so forth. And you could iterate this. So this is, in a certain sense, the easy part. And iota is order preserving and order reflecting. This is not particularly difficult to prove. Well, I mean, so with respect to the orders that I defined. So usual comparability on the side of sequences and the strange order on sets that I defined before. The problem here is in a certain sense that it has a rather small range, right? So by the way I defined it, all the sequences that I produce will be spectacularly regular. So in particular, it is not difficult to see that they will be indecomposable. I mean, so it is clear that I can forget about any initial segment of this sequence that I'm forming this way. I will still end up with essentially the same thing, which is basically means being indecomposable. And okay, we don't really care here, but so we do need countability in order to do something like this. Okay. The difficult part is to go the other way around. I mean, the trickier part is to go the other way around. So here I could do this with no assumption whatsoever on Q. So the fact that Q had to be a better quasi-order here did not show up. It will show up here. So if I want to move from sequences to sets, then I will need some more assumptions. So now given alpha and Q such that a big enough level of this iterated number of closed sets is a well quasi-order, then I can go back. In a certain sense. So I define the map eta as being, well, it's defined trivially on anything with length of successor, which basically, I mean, what it does is simply take the last element of V, and this is the only thing you care about. If you don't have length successor, you define it inductively as follows. So you have your V, you suppose eta to be defined on all the shorter segments of V, and you look for min of this set here. Now, the reason why I want this guy to be a well quasi-order is because if it is not, there's no reason for this thing to be a min. It will just be an inf. I mean, it won't exist in general. So, I mean, again, I could try to explain it to you, but let's just look at an example. So, if I take iota eta of 0, then I just end up with the element 0. If I take eta of 0 to the omega, what am I looking for? I'm looking for min of eta of sequences of length n, only taking value 0, and well, eta of sequences, of anything of successor length is, well, basically it's essentially defined here. So here I'm just looking for min of, over the set containing only the set containing 0. So indeed, it will be the set containing 0. The non-trivial example is basically when we have some initial segment. So like in a certain sense, this is what we care about. So if you try to apply eta to 1, 0, 0, 0, basically you see that by this procedure, you forget about initial segments. No, you need to prove it. So, right. So in general, being a well quasi-order would only tell you that it is a finite set. But by the structure of this thing, it is actually, it is a mean. So there's just one point. There's something else to be proved. But yeah, that is true. In general, you end up with something like this. So you take the mean of, I mean, yes, some values and the mean exist just because it is well quasi ordered, but there is more work to be done. So here we don't care, and right, so by looking at which the mean is attained, so we get this result, but we don't really care about it. So if Q is better quasi-order, then only the composable sequences, eta and iota, are inverses, but what we care about is much more general. So here I'm forgetting about alphas because I'm lazy, essentially. But even more is true. So if we change comparison, so let's say what we have seen so far is that provided Q is nice enough, and we restrict our attention to indecomposable sequences, then iota and eta are very well behaved. One is the opposite of the other, and they respect order both ways. But we can do much more if we change the comparisons of sequences. So if we introduce this new thing here, so we say that U is cofinally embeddable into V if for every tail V prime of V, I can find a tail U prime of U such that V prime regularly embeds into U prime. So basically I'm in a certain sense lifting this embeddability relation to just tails of things. Firmly a typo. Yeah, it's a typo. This should be U and this should be V. Oh. Thanks. Sorry. Yeah. Okay. Plenty of things to correct. Yeah, look. Okay. There's a lot of typos. But yeah, this one is a terrible one. Okay. Yeah, it should be U prime embeds into V prime. Sorry. And the point is that, well, essentially, so if you just restrict the relation on indecomposable sequences, this is just regular embeddability. And there's something more refined than this to say, but well, the nice result that we have is that actually, if you compare sequences with this relation and in downward closed sets with the regular relation, then this is exactly what you're looking for. So this is a categorical equivalence essentially between these two orders here. So iota of x cofinally embeds into U if and only if x is less than eta of U, and the other thing as well. Okay. With the assumption that we carry from before. So we want eta to be defined. So we need this guy to be well quasi-order essentially for alpha large is enough. Okay, so under this assumption, so assuming that I can apply this theorem, in particular it follows that U is cofinally equivalent, let's say, to iota of eta of U. And now this thing is indecomposable. So in particular, if you just unravel the definition, now I don't have the time to do the combinatorics, but you just unravel the definition. So if U has a tail V, you will have a tail V such that V embeds into something indecomposable, and that indecomposable thing also embeds into V, so V is indecomposable. So what we showed is that under this assumption is that every sequence has an indecomposable tail. But then if it has an indecomposable tail, it means that every Q sequence is just a concatenation. I can just apply this infinitely many times and every sequence can be decomposed. So indeed, if you believe me that all of these theorems can be proved in ATR0, we did reach almost what we wanted in the sense that we substituted the assumption of Q being better quasi-order with V of Q being well quasi-order. So this is the last step that we need to go through. But in a certain sense, we already did most of the job. So we only need to show that Q better quasi-order implies V of Q well quasi-order. And this is basically just the first part of the first theorem that I was proving. So the Nash-Williams theorem for finite range. And basically, this is the reason why I told you if Q was a better quasi-order, now we would be done. So that's the point where we stop the proof and we're happy in this case. Of course, there's some different in the setting here. So what we actually prove is something similar, so that I can constructively remove, let's say, so if I have a bad sequence into a big enough level of V alpha of Q, then I can move it into a bad array into, okay, not just as before, not just Q, but Q times omega. Because, let's say, morally, this is equivalent to have the issue with length that we had before. So we can also be precise about the alphas here. But so what we care about is basically the contrapositive of this. So that if Q is a better quasi-order, then in particular, this guy cannot have bad sequences into it. And again, so what we do is essentially the same proof as before. So we start with, we assume that we do have such a thing. We extend it to be something defined on omega to the less than omega, having some price to pay with respect to the range. So instead of considering your elements, we consider your elements times omega. And we still want to preserve badness. So, at level 1, there's nothing to be done. And at the next level, yeah, now there's basically, we don't need any combinatorial engine to carry out the proof. So what does it mean that h of n0, nk minus 1, and h n1 sk are in this relation here? It means, just if you remember the definition of the order Q, that there is an X inside of here, such that it doesn't matter how you pick Y inside of the other guy, you will not have comparability. And this is what you pick. So this is exactly the analog of picking the right in the composable sequence here. So you should still see, okay, yes, and you choose that X. As before, we define F the same way as before. And okay, so I'm skipping plenty of details, but by preservation of badness, we also have that this H of F is bad. And now this is a contradiction, because now we do know that Q is a better quasi-order because it was our assumption. Now, and we could also prove the other implication in a certain sense by reversing the process, by which I mean that if these guys are well quasi-ordered, this implies that Q is a better quasi-order, which is in a certain sense what you were, well, one of the, let's say, the non-reversal direction of what you were asking before. So this goes through in ATR0. So in particular, we do show that if Q is better quasi-ordered, if and only if V of Q is well quasi-ordered, which goes well in the way of what I was saying before. So substituting, in a certain sense, minimal bad arrayness arguments with well quasi-orderedness argument. And yes, this is a long list of references. This is all I wanted to tell you about.